So these are all equal recruitment patterns in terms of producing the same stable posture of the arm. They all will hold up the arm against gravity, maintain it in this position, but you can see here's a situation where I'm just using biarticular muscle at a low level of activity where I have to generate the torques opposing gravity. Here's where I just use a pair of monarticular muscles to do so. Here's where I use biarticular muscles, but now I'm highly co-contracting them so that I'm generating the same net torques at the joints, but with much more activation of both of the muscles, co-contraction. Here's co-contraction of the monarticular muscles, and here's a distributed pattern of co-contraction amongst all of the muscles. If I give my modeled muscle system the properties of constant torques, that is, assume that they're idealized torque motors that don't have any intrinsic properties, then obviously when these perturbations occur, the arm will be, the end point of the arm, the hand, will be pushed radically in different directions, more or less independently of the muscle activation. If I give the muscles a property that they have a force-length relationship, then I get, again, rather large perturbations because most of these perturbations are occurring over a range where muscles generate relatively little change in their force output as a function of length. What they do change is their property of force output as a function of velocity, and here you can see that these co-contraction patterns are quite effective in stabilizing the endpoint of the arm during the first 100 milliseconds of the perturbation. So each of these steps is 10 millisecond time epochs at the endpoint of the limb. And so you would learn to use different patterns of co-contraction. Anybody who's ever done this sort of thing knows that the first time you shoot, your arm kind of goes all over the place, and then you realize that you have to use certain patterns of co-contraction to stabilize it. So let's talk then about how you learn to use a system that has these incredibly complex nonlinearities buried everywhere within it. So a couple of general principles. First of all, that you have a rather large population of receptors that you use to achieve high resolution over what turns out to be a rather wide dynamic range. And you further improve that dynamic range by actually anticipating the operating point of the system. And we'll see how that's done with something called a fusomotor gain of spindles. The activity of all of these populations of receptors has to be integrated into some sort of state estimate of the condition of the system. And the feedback, as we'll see, is highly convergent, that we don't have a sort of simple servo control system here, but rather a system that tends to mix the different patterns of the different modalities of receptor and the different locations of receptor across the entire limb. So we'll figure out how that happens. So again, being able to make fast and accurate movements is essentially the fundamental thing that differs animals from plants. And so getting this right after you've gotten a system that has desirable efficiencies that are built into the properties of the muscle, of course, is impossible. Is necessary and important, and basically the systems that engineers have developed over sort of the last 50 years are the systems that physiologists have been trying to integrate into their understanding of how this might be done by the nervous system. And I think to a large extent that's not been terribly useful, and we'll talk about why that might be. A lot of what you find in physiological textbooks is sort of a warmed over version of 1950s servo control, which clearly isn't terribly useful for multi-articular organisms. And a lot of the optimal control and inverse models that are being used in robots such as we heard about this morning are probably not the sort of thing that the nervous system is geared up to compute. So we'll talk about maybe what is happening in there. So first, let's just mention the sensors that you actually have to work with. And the base, so there are a lot of them. The two that we're going to focus on are the proprioceptors that seem to be most important. And these are the hundreds of receptors that you have distributed throughout each muscle. So one of the important things to remember, people always assume that how are we doing for time? I can't see you. It's scaring me. so one of the things I often tell my students is, if you close your eyes, you know where your hands are. And you know where they are quite accurately, so that you can actually pretty much put your fingertips together. How do you do that? And you do so because your muscles have these hundreds of receptors distributed throughout them. There's over 10 times as much neural traffic coming back from the muscles to the spinal cord as there is control information going out, which gives you some idea of how important sensory feedback is to the performance of the system. The relatively simple structures are the force sensors, which are actually in series between a subset of the muscle fibers and the series elastic tendons, the collagen of the tendons, so that these are essentially responsive to the active force of samplings of the muscle fibers, which individually are quite random and highly nonlinearly related to the total force, but as an ensemble of 100 or so of these, sampling all the different combinations of muscle fibers, are actually remarkably linear as force indicators. The muscle spindles have a much more complicated structure. They're each about the size of a muscle fiber, which is about 0.2 of a millimeter in diameter. But inside each of these little structures is a whole complex of tiny little muscle fibers, specialized gain control elements called intrafusal muscle fibers with very specialized properties. And they're under control of a specialized set of motor neurons that just adjust the stiffness of the sensor. And they can shift so the receptors are wrapped around the central portion of these little fibers in various combinations. And by adjusting the tension in these different kinds of muscle fibers, you can radically shift the sensitivity of the spindle either to changes in length or to changes in velocity or any combination thereof, which is a useful thing in a system that has a very wide dynamic range and transducers that have individually rather limited dynamic range. So the signal transmission code in the nervous system is essentially binary rate code, and you can't, of course, fire neurons at less than 0 pulses per second, and you can't actually fire them at more than about 300 pulses per second because of the way in which they sort of regenerate their signaling capability. It's not useful to fire them at really low rates because then you have such a sparse code that you can't integrate over short periods of time and get an accurate measure. So the sort of real dynamic operating range is like 20 to 200 pulses per second. And you have this very wide dynamic range of lengths and velocities that you have to be sensitive to. So in mechanical systems, when you're designing transducers, we know that the transducer will have some low saturation and some high saturation, which is no longer sensitive. And you just assume that over the entire operating range of input signals that you might want to sense, that you would be best to have something that's linear over its available output range. And then just hope that its noise is low enough that you can get whatever resolution you need over that range of operation. It turns out that you can actually show that the optimal curve for a transducer is the integral of the probability of occurrence of various states that you want to transduce. Now, the biological system has as its big advantage that it knows what range of input signal it's likely to get, because it's largely doing self-made movements in familiar situations. So part of what you learn when you're performing a task is an expectation that if you're handwriting, for instance, your muscles will be operated over a low range of lengths and velocities. And if you're throwing a ball, then you'll be operating those muscles at high range of lengths and velocities. And so you can adjust the sensitivity to each of those components independently over whatever operating range by adjusting the properties of the transducer. And you do so essentially by assuming that you have a Gaussian distribution, the most likely circumstance that you expect if the system's noise-free and perturbation-free is there, and that there are these tails that you have to cope with. And so the optimal transducer property would be the integral of whatever the probability density function is of the states that you expect to be in. And of course, for different tasks, those states will change. They might get broader, they might shift to different locations, and you would want to tune the shape of the transducer so that its maximum slope sits at the center and it covers the range of states that you have to transduce. And the system actually seems very well set up to do something like that for the muscle spindles. Okay, so that's a very brief overview of the transducers we have to work with. How does the biological system put all this together? So one sort of simple way of relating very primitive engineering principles to this is that you have feed forward systems that basically are going to generate some control signal to the actuators to produce a movement, and then there are feedback systems that try to maintain stability of a state by feeding back sensors to some sort of a servo mechanism. And you could look at the biological system and say, well, maybe that's the way it works. Motor cortex is the feed-forward system that turns on the muscles to generate movements, and then we have this proprioceptors that come back in the spinal cord, generate things we call reflexes. This is when you go to the doctor's office and they tap on your knee. That's actually a little sort of snippet of information about one of these reflex pathways in which stretch of the muscle produces a positive feedback that causes the muscle that was stretched to pull back by activating. And that's a nice story, but it's completely wrong. It turns out that almost none of the activity from your motor cortex, the main source of voluntary drive, to the spinal cord goes directly to the alpha motor neurons that actually control the muscles. Instead, it goes to the interneurons, which are the same interneurons that are getting the feedback information for generating these reflexes, and a lot more. In fact, they get information from both the length and the force feedback from multiple different muscles and converge them, often from muscles that are either antagonistically arranged across the same joint or muscles that are operating at joints that are not even adjacent to the joint at which a muscle is receiving its feedback. You get these highly controlling convergent and divergent patterns. And so we've elected to think of this thing more as a programmable regulator. And in industrial design, one often uses a regulator, a multi-input, multi-output system in which you set up a matrix of gains to achieve whatever performance you want in the system. The state of all of these gains is apparently what's being controlled by the brain, and that's causing the system to elaborate the dynamics of the movement you want to perform. So just how difficult is it to figure out how to set up all those gains rather than to compute the actual activations of the muscles that you want? So that the dynamics of the spinal cord, after you've set it up, is what actually elaborates the dynamics of the movement rather than having to send a lot of detailed information about the timing of muscle activations from the brain, which would probably not be a good idea because the brain's a long distance and distance takes time. Feedback loop delays in the biological system are really bad news. The beautiful performance you saw this morning with sort of centralized impedance control, if I told them to put in an 80 or 100 millisecond delay into their feedback loops, probably would have problems, and that's what the biological system has to cope with. So, our first attempt to understand the controllability of the system it was to model a very simple system that had at least some interesting complexity, and that is the wrist. So you could imagine an idealized version of the wrist in which you have muscles that can produce extension and flexion, and you have muscles that can produce radial and ulnar deviation. So it's a 2-degree of freedom system. And you actually have 4 principal muscles that generate this that are arranged so that the muscles produce movements at essentially 45 degrees from those 2 canonical axes. And so we can think of what combination of muscles you would use to create any movement or any state of external force that you want. So we built up a model of the physiological properties of these muscles and their proprioceptors into the system. And then we also put in the known circuitry of the spinal cord. Now, it turns out for about the last 100 years, people have been mapping out the projections between all the proprioceptors and all the motor neurons through these interneurons. And so there are classes of interneurons that have different combinations of connections. So this one, in fact, is that stretch reflex that you get when you tap on the leg, that you have the stretch receptor in a muscle that has a positive excitatory loop to the alpha motor neuron that controls that muscle's contraction. But it's part of a system that also has projections to the antagonist muscle via an inhibitory interneuron. So not only do you activate the muscle that you've stretched, but you inhibit the muscle that would tend to block the activation that you just generated. That's an obvious sort of servo-like mechanism in a push-pull system. You have another system that provides negative feedback, a sort of governor-like function in which the activity of the alpha motor neurons to the muscle feeds inhibition back onto the pool of alpha motor neurons. But again, there are distributed connections from synergists and antagonists that cause widespread effects of this efference copy signal. There is a force feedback system in which the force sensors produce what seems to be a servo-like control that is inhibiting the alpha motor neurons that produce force in the muscle, so that you could imagine this loop stabilizing force. But there are widespread projections from synergists and antagonists in that system as well. And there's a propriospinal system, which is probably one of the most important ones in terms of being controlled by the brain. And this is a system that actually has convergent excitatory input from the length and the force sensors, causing excitatory effects on alpha motor neurons, but again, widespread effects on other muscles. So if you put it all together, you get a mess that looks like this for the pair of muscles that are diagonally oriented. So they must always be acting as antagonists, right? So one of them pulls up and over, and the other one pulls down and the other way. So they're always essentially antagonists. But then we've got the other pairs of muscles, so the two pair of muscles that can both pull up, one pulls up to the right and one pulls up to the left, so they're being used as synergists when I move this way, but they're being used as antagonists when I move this way. And so we have to have circuits that can allow them to operate in both their synergist and antagonist mode. We add the other circuits, and then you see a set of descending controls to operate the sort of bias points of all these different interneurons, and a lot of little gain adjustments that can be made at every one of these strength projections. And so essentially the brain's job is to figure out how to set all of these adjustable gains and biases to get the system to do what you want. And we started with the very simple assumption that the brain could get to the state that it wants with no specification of dynamics at all. Basically, that all you could do was set some background level of gain to maintain, say, stability in the system, and then if you wanted to make a sudden ballistic movement, say a force pulse or a movement, that you would just have a step change in the gains. And now in the new state, all the dynamics that you need to make the movement, to accelerate and decelerate and stabilize the joint, would be elaborated by this circuitry, which has the advantage of being able to work quite fast because it's close to where the periphery is. One last thing about the property of all of those points is that where they come together at these interneurons, the interneurons have basically that sort of input-output function, because each of them is really a population of cells. And even if the individual cells have a sort of a linear firing rate versus their driving potential, and then they saturate, a population of these all starting at different potentials would have an approximate input-output relationship that's sigmoidal. And that's important because what it means is that one input effectively produces a gain change in another input. Right, so a step of a given size, if I'm operating at this part of the curve, has a very different effect on the gain as a step of the same size if I happen to be already biased to another point in the system. So here's our system. We're going to try to create movements in this very simple system with only 4 muscles and the various proprioceptors. and the fusomotor systems that control those proprioceptors, and the gains of all the interneurons, there are 184 gains that have to be set, which look to us like a hopelessly complicated problem, even if we restrict it to only producing this background activity and then this sudden change in state when the go comes along. So we asked ourselves, how difficult would it be to get a system like this to converge to the desired behaviors? And we took an extremely simple learning algorithm, and I may have a chance to talk about a slightly better one. In this case, we just said, well, let's take each gain. We'll start with all the gains randomized. Performance will be terrible. We'll have some cost function based, say, on the position or force that we're trying to achieve. And we will just take each gain one at a time at random and step it up, step it down, and pick if it's better, whichever state is better. And so you go around all 184 gains, test each one up and down at random, but you pick the best one for each of the tests. And we call that one iteration of the model. How long would it take a system like this, operating 184 dimensions, to come up with useful behaviors? So the first thing we picked is simply getting the system stable in response to one of these sudden perturbing forces. So there's a brief force pulse that occurs at a particular point, and the system, without the spinal-like regulator, simply its passive mechanical properties, has, of course, this highly underdamped oscillation. And when you get the spinal-like regulator turned on to a good condition, you get a behavior in which you get these phasic activation of the stretched muscle and then the antagonist muscle, which stabilizes the position. Now that should come on. Yes. So that just shows the system's response to a perturbation, which is in fact similar in terms of the angular change and the recovery back to zero baseline and lack of overshoot to the sort of profile that you actually measure in a human exposed to the same sort of perturbation. And you also see similar phasic activity in the muscles, in the motor neurons, and in the force that's actually elaborated by those muscles during the response to the perturbations. So here's a slightly more ambitious task. Now we are maintaining stability initially and then asking the system to go as rapidly as possible to a new angle and hold at that angle and then resist perturbation at that new position. And so when this step comes along, we see phasic activity first in the agonist to get it accelerated upward, then in the antagonist to break it at that level, and then this phasic agonist-antagonist burst if the system is perturbed. And again, the behavioral response of the system is a nice, crisp joint angle change and a response to perturbation that looks very satisfying. And the speeds and stability are about comparable to a human asked to make exactly that sort of movement. Another thing you can do with this system is, rather than producing an overt movement, is that you could ask the system to produce a force step. And this is some experiments that were done by Claude Guez and Jim Gordon some years ago, in which people are asked to make a sudden motion to a force plateau, and you have to go as quickly as possible to that level of force, but not overshoot. Or you can go up to that level of force and then let it decay. Both of these are actually a lot more difficult than it seems, because to move the force level as quickly as possible, you have to deal with the fact that the muscles respond very sluggishly. And so if you just turn on the agonist and you try to get up to that force level without overshooting, you'll come up very slowly. And to go as fast as possible, what you do is you overshoot with the agonist, and then you turn on the antagonist at exactly the right instant to compensate for what would otherwise be an overshoot of force, and you get that sort of behavior with this very phasic activity. Again, this is isometric, and so there's not any overt motion of the limb. And in this system, the system of adjusting the interneuron gains and giving it this rather simple background activity and then a step in some change of the gains produces performances that really look very much like the biological system, going to a force plateau or going to a force pulse. And again, if you allow the system to make the force step at a much slower rate, the system then only activates the agonist muscle, just as the biological system would do, and doesn't need this antagonist burst. Excuse me. So let's pick something that's even harder. This is a task that physiologists have gotten rather interested in because they feel it's an indication of a sort of central internal model of the properties of the external world that presumably the brain would have to learn to compensate for. So this is what's called a viscous curl field. It's viscous because the perturbing forces to the movement that you're trying to make are proportional to the velocity of the movement that you're actually making. And it's a curl field because the perturbing forces are perpendicular to the direction of motion. So you try to go this way, and the faster you go this way, the more it pushes you laterally. And so, again, we have this very simple step function that has to learn to set up the interneurons to compensate for now this very complicated set of dynamics. And sure enough, the system seems to do so. So this is the behavior of the system initially with all those gains randomized. And of course, it's completely spastic when trying to make that movement in the curl field. And then after we've optimized the settings of the gains of the spinal-like regulator, it makes a rather nice straight movement with very little deviation. And then if you turn the curl field off, you get an after effect, which is exactly what humans do. So if the humans have learned to make this movement by compensating for the curl field, and you suddenly turn the curl field off, then they, of course, make a compensatory trajectory as if the curl field were there, but now they overshoot in the other direction. And again, this is done with a brain that is no more capable than just generating step functions. So the question I posed earlier was, how long does it take this system with 184 dimensions to figure out how to set all of the gains? And so for each of the 5 tasks that I just showed you, this is the cost of when we start the behavior. And so these are very high costs because it's a completely spastic, random set of gains in the system. And after one iteration, that is one pass around the 184 gains, it's already down to quite stable levels. And with repeated iterations, there's relatively little further improvement. And these are actually all about or below the typical kinematic costs that a human would have performing these tasks. Now, of course, this just represents one learning of the task, and I could say, well, if I start with randomized gains, of course, I'll have many iterations of learning. So here's 10 times I perform the task. Sometimes I actually start with gains that are not too bad. Most of the time, they're really terrible. But every time, it converges to solutions that are basically good enough in terms of human performance, but they converge to what appear to be rather different solutions. And if you take apart a couple of these solutions after they've converged and you look at the individual gains, so that's just a subset of the gains in there, you see they're wildly different. What does that mean? Well, this is a system that seems to have many good enough minima distributed throughout its workspace. What the biological system can do here is take advantage of the fact that this really complicated plant and these really complicated interneurons have evolved over hundreds of millions of years to actually give you lots of good solutions to lots of problems. And so you don't have to have an internal representation of the plant and invert it. You couldn't. I mean, think about the complexity of the circuitry and the muscles we've just talked about. There's just no way you're going to invert that plant and figure out what to do. Instead, you rely on the fact that by trial and error, fairly quickly, you can find solutions to problems because the set of components you have to work with is designed such that the space is full of pretty good solutions and tends not to have local minima that you get trapped in where you're stuck with an unacceptable solution. Exactly what, why that's true, we don't know, but you could obviously see the survival value. The biological system is not designed to find optimal controls. I mean, you only have to be globally optimal if you're planning on getting the gold medal in the Olympics, and that's not what we evolved for. What you evolved for is to quickly solve problems good enough so that you can, catch the thing you're going to eat or get away from the thing that's going to eat you. Yes? So what's interesting is that the activation at the level of the muscles that you see tends to be quite similar. Basically, and especially if you add energetics terms, which we hadn't yet at this point. And that turns out to be more important, as you'll see in a moment if we have time, when you get to linked systems where you have Coriolis effects. This wrist system we cleverly chose doesn't have that problem. It's got two joints, but they're concentric. As soon as you get to linked segments with Coriolis effects, then yeah, it turns out that energetics is really an important consideration. So in any event, the system tends to find solutions that from all the things you could measure on the outside, like when the muscles are active and how much force they're generating, look similar. But the internal states that they use to achieve that same overt visible behavior are remarkably different. And that has implications if you go to learn a new task. Because what you probably do when you're faced with a new task is you start with something that you've already learned, which is similar. And then you try to shift it to deal with the slightly different performance criteria. And it may well be that the starting points that are otherwise identical are actually different in how quickly they can be shifted to deal with a new task. And anybody who's ever coached sports or tried to take up a new sport in a group knows that people who appear to be normal, appear to be identical, appear to have similar athletic ability will sometimes catch a new sport really quickly and sometimes flounder around for a long period of time. And I suspect it's because their internal states are actually rather different. They've learned different ways of doing the task. And some are closer to the new task than others. Yeah. Yes. Well, I mean, there's no question. I can certainly define a cost function for which there will be a global minimum. And the question is, does the biological system ever find it? And does it even care? And under most circumstances, it doesn't care. It basically gets, so all of these are distinctly different solutions. And this one is an order of magnitude better in its cost function than that one. But they're all so far down, this is a log scale, that they would all be considered equally good unless you sort of redefine what's good enough performance or brought in some other axis. In this case, it's only the kinematic costs, but we could have added the energetic cost in the system or the robustness in the face of perturbations or noise, which are also critical. But I think no matter what you put into your cost function, I think the biological system is essentially doing a random walk through a set of gains until it finds something that's good enough. And then it saves that as part of your repertoire and uses that for starting points for anything that's similar. So defining the cost function is absolutely crucial. And as we started to see when we got into these linked segmental systems, that if you don't define the cost function to actually properly consider all of the possible costs, you get nonsensical solutions where the system performs well, but just because you have, so you get, for instance, circumstances where you get unrealistic amounts of co-contraction if you don't include energetics just because it works for the task. So yeah, I absolutely agree that you can use all the usual tools to evaluate the solutions, but I don't think the biological system is playing the game from the engineering perspective. So you would like me to finish?
Well, everybody who wants to have lunch,
yes, and I
should
certainly don't want to stay with.
Go there.
So
just about
I'm going to just. So I left a very large amount of material, which I'm not obviously going to show. But what I want to just say, leave you with two things. First of all, we like to draw the distinction between anthropomorphic design and biomimetic design, and I suspect most people in the room have a similar sort of view. There is something called anthropomorphic design in which people just try to make it look exactly like the biological system and hope that that's somehow useful. What we think is much more useful is to identify the utility of each of the biological design features. So they're there, and the question is, what are they good for, and do you care? And can you achieve, if it's useful, can you actually achieve a similar function with engineered materials or control loops, and then show that including that actually enables some capability that you'd like to have. What I want to, yes. Okay, so this afternoon I want to do two things. They won't be quite what I had originally hoped because it turns out that the software that we have available, this musculoskeletal modeling software, needs the MATLAB toolbox, but also with the sim mechanics. And I guess most people here don't have a PC with MATLAB and sim mechanics in the toolbox. If you do, you can download and follow along with the simulation we'll run this afternoon. But we've incorporated into a very user interactive way all of these internal models of the muscles and their properties and ways to build up complex systems, including the proprioceptors and their gains and all of the biological properties into systems that you can then convert into a Simulink block and put into control loops to see how they behave if you want to play with the biological system. And the other thing I will do at the beginning of the session is talk about something completely different, give you a little demo. I couldn't resist the opportunity to shamelessly promote our product that came out of our laboratory called the BioTac, which is a biomimetic tactile sensor. So we got all these roboticists here who have probably started to realize that getting robots to have a sense of touch is actually rather critical. And we have, so this company called SynTouch has commercialized this tactile sensor that essentially has all of the modalities and the dynamic range of the biological fingertips in a rather robust package that can actually be used in the field with real industrial robots. And so I'll give about a 15 or 20 minute demonstration of that technology for anybody who's interested in it at the beginning of the session, and then we'll mess around with the musculoskeletal modeling software, which I can show as a demo on the screen and you can download later if you have the right tools. Thank you.
Thank you very much.